Okay. So last time we started talking about L'Hopital's rule. We are going to actually formulate L'Hopital's rule today, and then we're going to do a bunch of examples, and you'll have some time to work on the practice set that I've posted. You're going to see the examples are always more or less the same type of example of problem, and so there's really not that much to there's really not that much to this section. It's just a matter of practicing, how to identify the different pieces in an exam. So what I have is the following. L'Hopital's rule. L'Hopital's rule. Rule tells me the following, which is that we can suppose that f and g are two differentiable functions on a given interval I. Okay, so two functions that are differentiable on an interval I, although not necessarily at A. Okay, so I'm not going to write that down because it's really not going to happen that frequently, but just so that you keep in mind, we could have the exception where the function is not differentiable exactly at a given point. In an interval I, and the interval I contains a value A. Okay, so it contains the number A. We also are going to assume that the derivative of the function g of x is going to be different than 0. So I'm going to write equal, but I'm going to cross it later with my pencil. So just write different over there. Different than 0 for all values of x in the interval I. Okay, so suppose that f and g are two differentiable functions on a given interval I containing A. I forgot how to English. And g prime of x is different than 0 for all x in that interval I. Then, if we have the following, so here's where I start writing. So first thing is g prime is different than 0. Okay. So if we have that, the limit when x goes to A of f of x over g of x is of the form 0 over 0, then we'll get that. We know that we can't evaluate this limit because it's an indeterminate form, 0 over 0, and so that means we're going to go instead and evaluate the limit as x goes to A. But now instead of evaluating it for f of x over g of x, we're going to evaluate it for their derivatives. So instead of evaluating the limit for the ratio between the functions, we're going to evaluate the limit for the ratio between their derivatives. Remember, so this is the last thing that we did last time. We did one example, and then today we're just formulating the same thing that we did. All right, so this is what we did last time. There's one little difference that we're going to consider today. So one thing that we're going to add, which is the fact that this rule can be applied if the limit is of the form 0 over 0, or this can also be applied when the limit, when x goes to A, of f of x over g of x gives me an indeterminate form, which is infinity over infinity. Of course, here this is all in quotation marks because there's no such thing as 0 over 0 or infinity over infinity. Does this make sense for everybody? Okay, the reason that this is also applicable in the case where we have infinity over infinity is that infinity over infinity is like saying 1 over, and here again, quotation marks, because I'm not doing actual algebra here, it's just a way to understand it. Infinity is the same as 1 over 0, and then infinity at the bottom is like saying 1 over 0. And so when we have an expression that is of the form infinity over infinity, this is equivalent to some other expression, which is also of the form, if I multiply these two fractions, of the form 0 over 0. So when I talk about infinity over infinity, I'm also talking about 0 over 0. They mean the same. All right, do I have any questions about this? All right, so we're going to do a bunch of examples, and that's going to be the lesson for today. We're just going to do a bunch of practice with L'Hopital's rule. I think I have 6 examples that I want to cover in today's lecture, and then you can go to the practice set number 11 in order to practice this. So in the following example, I'm going to ask you to evaluate the limit. So evaluate the limits, which are the first one. So last time we did the example with limit when x goes to 0 of e to the x minus 1 over 2x. Today we're going to start with the following. Limit as x goes to 1 from the right. So 1 plus of sine of pi times x divided by square root of x minus 1. So a couple of things before I let you try this problem. The first thing that I want to ask you is, what does it mean, this 1 plus over here? What does 1 plus here signify?
It's the limit coming from the right.
Limit coming from the right, which means limit coming from values of x that are what?
Greater to lower?
Greater to lower. So they're greater than 1 and they're approaching 1. So I think from this side, you're looking at it like this, right? So that means you have 1 over here. And if you're coming from the right, then that means that you're approaching 1 by values that are larger than 1. So that means 1.1, 1.01, 1.001, and so on and so forth, right? Why do I need to make sure that this is coming from the right? What would be the problem if I allowed x to also come to 1 from the left?
You won't be able to find an answer.
Why?
Because it's going to divide over 0.
So it's going to divide over 0 regardless, but over here, by saying that this is going to be plus, I'm guaranteeing that the denominator actually can be evaluated, right? Because I have that if x is coming to 1 from the right, x is a little bit larger than 1, just a tiny little bit larger than 1. And so x minus 1 is going to be a little bit larger than 0, right? So by guaranteeing that x is coming to 1 from the right, I make sure that the root is being taken out of a number that is approaching something that is positive, right, and not something that is negative. Can I see a show of hands for those of you who understand this? All right, so again, because x is larger than 1, so it's 1 and a little bit, so 1.01, let's say, then when I subtract 1 from this number, from x, then I'm going to have a number that is going to be slightly larger than 0, right? And because it's slightly larger than 0, then I can evaluate the square root of that number. All right, so now let's try to plug this in and see what we get. So by plugging in, by just substituting directly into the limit, we're going to get that this is the same as sine of pi divided by square root of 1 minus 1. Maybe 1 plus, just so that we remember that we can actually evaluate that. Okay, again, this is like equal to, because this is not going to be a number that we can evaluate. Now, sine of pi, if you remember correctly, so pi is the angle that ends up being just here. So we just saw that. Pi in radians is this angle over here, which means that sine of pi is sine of this angle over here, and that's the second coordinate of that point, right? So sine always gives me the second coordinate. So that means that sine in this case is going to be equal to 0. Okay, so that means sine of pi is equal to 0. And then this is divided by 0 as well. Now, if you don't remember how to do this using the trigonometric circle, that's perfectly fine. You can use your calculator regardless. You could use your calculator under normal circumstances, and now you're at home. So honestly, I'm not going to be verifying that you can use your calculator. It's just a matter of understanding why this value would be equal to 0. Yes, Galen, there's a question? No question. All right, so this is 0 over 0, which means that this is not going to work. I can't evaluate my limit like that. I have to do a little bit more work. And so because of this, we're going to try something else, which is to use L'Hopital's rule. Okay, so L'Hopital's rule. So with L'Hopital's rule, I still have that this is going to be the limit as x goes to 1 from the right. And now I'm going to take the derivative of the numerator and the derivative of the denominator. Right? So derivative of the numerator is going to be the derivative of sine of pi times x. So the derivative of sine is cosine of the inside function. But then because the inside function is not just x, I know that I'm going to have to multiply by the derivative of the inside, which in this case is pi. And then the derivative of the denominator over here, well, maybe I can rewrite it just on the side. This is the same as x minus 1 to the power of 1/2. And so if I differentiate that, I'm going to get 1/2 times x minus 1 to the power of -1 over 2. Right? And so what I'm doing here is really just identifying what the numerator is and then differentiating that numerator, and then identifying what the denominator is and then just differentiating that denominator. Keep in mind here, you also are applying a chain rule. It's just that the derivative of the inside is just 1. So okay, then I'm going to try to simplify this. So I'll have limit when x goes to 1 from the right of, now this 2 is at the denominator of the denominator, which means I'm going to put it at the numerator. Then I have pi times cosine of pi times x. And then I have x minus 1 to the power of -1/2 at the denominator. And so if I want to get rid of the negative exponent over here, all that I have to do is put this term at the numerator. And so this is times square root of x minus 1. Can I see a show of hands for those of you who understand all of this?
Unless I got lost in the last part you did.
Okay, so the derivative is okay. Can I see a show of hands for those of you who understood everything I did to find the derivatives? Okay, so derivatives seem like they're okay. Now, what I'm doing over here is just writing everything together, right? So try to simplify the writing of this. So to do that, I start by writing, okay, so I have the cosine of pi x, that's here. Then I have pi, which is also here. But then I have 1/2 at the denominator, right? And I know that 1 over 1/2, so if I have the denominator of the denominator, that's the same as putting it as a factor of the numerator, right? So like 1/1/2, something that's, if I'm dividing the denominator by 2, that means I'm multiplying the whole thing by 2. And the same thing over here is x minus 1 to the power of -1/2. Because this negative power is at the denominator, when I put this term back at the numerator, the exponent is going to become positive. So I'm going to have x minus 1 to the power of 1/2 at the numerator, which is the same as square root of x minus 1. Is that good? Show of hands for those of you who understand this. Okay, I can see chat. Okay, good. All right, okay, so at this point, we have now found the derivative of numerator and denominator, and we can actually try to plug in again, right? So we can see if our L'Hopital's rule actually helped me in evaluating this limit. So I'll have 2 times pi times cosine of pi times square root of x minus 1, which is 1 minus 1. And this is the same as 2 times pi. Cosine of pi is the first coordinate of this point, so it's going to be -1. If you use your calculator, you're going to find the same thing as long as your calculator is set to radians. Remember, radians, always, always, always. So this is -1. And then times square root of 0, which is just equal to 0, and my limit is equal to 0. Does everyone understand this? I have Matthew with your hand up. Is that because you forgot or because you have a question? All right, so the answer over here is I didn't know how to evaluate the limit originally. I got an indeterminate form. I used L'Hopital's rule, and then I found that my limit was actually equal to 0. So my conclusion over here is that the limit as x goes to 1 from the right of sine of x times pi, sine of pi x divided by square root of x minus 1 is equal to 0. Do I have any questions? Going once, going twice. All right. So next example. We have the limit as x goes to plus infinity of x to the power of 3 divided by e to the power of 2x. All right, so again, first thing that you need to do with any kind of limit example, and this is regardless of whether you're in calculus 1, calculus 2, or whenever in your life, is to try to evaluate the limit by plugging in. If that doesn't work, then we try something else. So by plugging in this case, what we want to do is reason out what happens when x is really, really large. And so if I have a number that's really large, let's say 1 billion, right? And I take that number and put it to the power of 3, then I'm also going to get a number that is really, really large, right? So that means that the numerator is going to be going to infinity. Then, if I take, again, my number that's really large, like 1 billion, and I evaluate e to the power of 2 billion, that's going to be gigantic. It's going to be really, really large as well. And so the denominator is also going to be going to plus infinity, right? And so I'm going to have an answer that is of the form infinity over infinity. And this has the same exact problem as when we have 0 over 0, which is that I don't know whether the numerator or the denominator is going faster to infinity. And so I don't know what the answer is actually going to be. I don't know if this will converge to a number. I don't know if it will go to 0, or I don't know if maybe the numerator is going to infinity way faster. And so that means that the result is going to be infinity itself. I don't know. And so I'm going to have to do some extra. Is this okay for everybody? Yeah. So because this is infinity over infinity, I can't evaluate it right away, and I need to use L'Hopital's rule. By using L'Hopital's rule, I'm going to have to take the derivative of the numerator and the denominator. So I'll have limit when x goes to plus infinity of the derivative of x to the power of 3. And here, please, 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 give the right answer. You know how to take this derivative. You know even how to take the antiderivative. So we might as well just, they should be really, really straightforward. And so this is 3x squared. And I'm going to divide that by the derivative of the denominator. And here there's always that little trap of the fact that the inside function is not just x, right? So that means the derivative is going to be e to the 2x, but because the inside function was 2x, I'm going to have to multiply all of this by 2. Is that okay? Raise your hand if you understand this. Good, okay. So once again, now I have tried to evaluate this by using L'Hopital's rule. Now that I've differentiated the numerator and I've differentiated the denominator, so this was the numerator, it gave me that derivative. This was the denominator, it gave me this derivative. As soon as I find the derivative, I'm going to try to plug in again, because that means that my the L'Hopital's rule should have made this easier to evaluate, and so that's what I'm going to try to do. So I'll have, if I have a very, very large number, let's say 1 billion, and I have 3 times 1 billion squared, I'm also going to get a very, very large number. And if I have a very large number, let's say 1 billion, and I evaluate 2 times e to the power of 2 billion, this is also going to be gigantic, and so I still end up with infinity over infinity. Does this make sense for everyone? Yeah. All right, so again, I'm going to put quotation marks over here because this is not an actual number. And so that means that I haven't done much work. I ended up with infinity over infinity again. Does anybody have an idea of something else that I could do if I wanted to evaluate this limit? What should I do next?
Second derivative.
We can do a second derivative. We can try this again because, well, 2 things. First, I don't know what else I could do. And second, well, you have that this is 3x to the power of 2, and so eventually I'll be able to differentiate this up to just getting a constant. And so ideally, I would end up with that because then I wouldn't have just infinity, right? So let's see if I can do the same thing. I'll have limit when x goes to infinity of 3x to the power of 2. I take the derivative of that, I get 6x. And at the denominator, I get 4 e to the 2x, because I take another derivative of e to the 2x, which brings a second 2 in front of the exponential. All right, I try to plug in again, and I get that 6 times a very large number is also going to give me a very large number. And 4 times a very large number is also going to give me a very large number. And so here again, I get infinity over infinity. Let's not despair. This looks like it's getting simpler and simpler and simpler at every step. And so I might be able to simplify things if I just take another derivative. Right? So I'll take the limit as x goes to infinity of 6x, which is just 6, and then the derivative at the denominator would be 8 e to the 2x. And now things have changed, because now I have that the limit as x goes to plus infinity is the limit of the numerator is just going to be equal to 6. And the limit of the denominator is going to be 8 times a very large number, which is going to be a very large number itself. Now, if I'm dividing a constant like 6 by a number that's really, 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 really large, what am I going to get? What is the result going to be?
Zero.
There you go, 0. right? Because we have that the denominator is becoming gigantic. So maybe like 8 times e to the power of 2 billion. That's going to be billions of trillions of, I don't even know what those numbers are called. And so you're going to get 6 divided by a gigantic number. If you have 6 apples and you divide them between everyone that's on Earth, each one is going to get essentially nothing, right? And so that means you have a finite number, just a constant, divided by a very, very, very large number that's going to always give you 0. And so that means that I can conclude the original limit that I was evaluating, which was the limit when x goes to plus infinity of x to the power of 3 divided by e to the power of 2x, whoops, this is going to be equal to 0. Show of hands for those of you who understand this. Good. So next one. Limit when x goes to 0 from the right of x times ln of x. Okay, so you can write it down and you can try to evaluate this on your own. I'll give you 1 minute to finish writing this down and then I'll start showing this problem. All right, so first thing is, what is the limit of x when x goes to 0? Everybody knows that is equal to 0, hopefully. And then we have to evaluate the limit when x goes to 0 of ln of x. And here is something that you need to remember, which is the fact that the logarithmic function looks like that, right? Where this value over here is equal to 1, because I know that ln of 1 is always equal to 0. Okay? Now, what we have is that if x is approaching 0 from the right, what's happening is that my function is going down like this, right? And so if I look at what's happening to the value of y, I'm going to get that the value of y is going to be going to what value? What is going to be the limit of ln of x when x goes to 0? So the closer I get to 0 over here, the value of y is going to get what? Anyone?
Minus infinity.
Minus infinity, right? So the closer I get to 0 over here, the further down this arrow is going to go, and so the value of y is going to be getting closer and closer to minus infinity, right? I'm going to, if I were to continue this completely like that, I would end up with something that's like this. It has an asymptote at 0. Okay, so that means that the limit over here is going to be minus infinity. Okay. My advice here is that you remember this drawing. Okay, so that you remember the graph of the logarithm. There's not that many graphs that you need to remember. For this class, you're going to have to remember the sketch of ln of x, and for the next couple of sections, the sketch of e to the x as well. So we're going to go back to that in a bit. But for now, we can remember that the graph for the logarithmic function looks like this. Right, so this is y equals ln of x. All right, so we have 0 times minus infinity, and that's a problem because I don't know what this is going to be. Which one is larger, the minus infinity, or is this getting closer to 0? If I have something really, really tiny multiplied by something really, really, really large, then that means I don't know what the result is going to be. Maybe the thing is so tiny that it will cancel out how large that big term is, or maybe the plus infinity is so large that even the tiny bit that is 0 is not going to compensate for that, right? So I can't know if this is going to be equal to 0 to some number or to plus or minus infinity, right? I'm going to have to do a little bit more. Now, lucky for me, and this happens a lot, 0 times minus infinity can also be written as either 0 over 0 or infinity over infinity, right? And that's because if I have 0 over here, that means that I have, so like if I have 0 times infinity, this is the same as writing the 0. I could rewrite it as 1 over infinity, and then this would be times infinity. So that means I would get infinity over infinity. So a large number divided by a large number. Or I can write 0 times infinity as 0 times 1 over 0, because a very large number can be expressed as 1 over a very, very tiny number, and this would be equal to 0 over 0. Can I see a show of hands for those of you who understand how I got to these equations? Okay, that's really good. And so I need to make sure that I'll get one of these two forms, because so L'Hopital's rule over here only allows me to use this rule if I have 0 over 0 or if I have infinity over infinity, right? So I need to get one of those two forms. Now, what that means is I'm going to have to write one of these as an inverse function. And so here's what I'm going to do. Okay, so I can erase this now. This was just for the idea. You can write it in your notebooks, but the main goal is for us to write this as either 0 over 0 or infinity over infinity. Now, I can write this as one of two ways. I know that this is limit when x goes to 0 plus, and I know that I'll either have to write x, which is going to 0, as 1 over infinity, or I have to write ln of x as 1 over 0. So there's two options. I could either write this as 1 over x times ln of x, or I could write this as limit when x goes to 0 plus, again, of x times 1 over ln of x. Can I see a show of hands for those of you who understand how both of these expressions are equal to the expression that I have at the beginning over here? Okay, so if I have 2, does everybody agree that this is the same as 1 over 2? Can I see a show of hands for those of you who understand how this is true? All right, now everybody lower your hands. Now, from having this idea over here, can everyone understand how x would be the same as 1 over x? Can I see a show of hands for those of you who understand how I've rewritten this now? Okay, that's a little bit easier, right? If we have an easier example to understand. Well, the same is true over here, right? We would have x times 1 over ln of x, right? And so this is also the same exact idea, but applied to the second term instead. In this case, we would have limit when x goes to 0 plus of ln of x over 1 over x. Whereas in this case, we would have limit when x goes to 0 plus of x over 1 over ln of x. All right. Now, one of these is going to give me 0 over 0. One of them is going to give me infinity over infinity. But before I decide on which one to use, let's look at this. If I were to use L'Hopital's rule in each one of these expressions, that would mean that I would have to take the derivative of the numerator and the derivative of the denominator for each one of these two expressions, right? This is already good because I now have a numerator and a denominator to differentiate, which means I'm already in the framework of L'Hopital's rule. The problem over here is that one of them makes it easier to differentiate than the other one, right? So for example, if I were to differentiate this expression at the numerator, this is easy to differentiate. Can I see a show of hands for those of you who know how to find the derivative of this numerator? Okay, good. And can I see a show of hands for those of you who know how to differentiate this denominator? All right, so just from looking at these functions, it looks like I can differentiate the numerator and I can differentiate the denominator. Let's look at the right-hand side. So like at the second possible expression. The numerator over here is also really easy to evaluate, right? It's really easy to evaluate the derivative of x. Now, the problem is that the derivative of 1 over ln of x is going to be slightly trickier because I would have to use chain rule. This is my expression for chain rule. Chain rule. There you go. Right? So here you would have to use chain rule. And so there's really, I mean, it looks like it's going to get probably a little bit more difficult to evaluate this expression, right? Because it's already getting more difficult, whereas I know that these two are very easy to evaluate, I'm going to say, you know what? I'm going to forget about this one. And I'm going to go ahead and just use the first case that I have over here. Hopefully it will make things easy. Show of hands if you understand this. Okay, I still see maybe like 9 hands that didn't come up. Is there anything that's not clear about this? All right. So I'm going to go with this expression. I'm going to see what I can do. So I know that the limit as x goes to 0 plus of ln of x, this is the arrows that I have over here, is going to be equal to negative infinity. And the limit as x goes to 0 plus of 1 over x is going to be, okay, well, as x goes to 0 plus, this is going to go to 0, and both of these terms are positive, which means that the denominator is going to be going to plus infinity. Does everybody understand this? Show of hands for those of you who understand how I got this denominator. Okay, keep your hand up if you raise your hand, please. Okay, is there anyone that does not understand how I got plus infinity here at the denominator? Everybody lower your hand, and please, if you didn't understand how I got the denominator here, could you please raise your hand? Okay, so what I have is x here is going to 0 from the right. So that means that this is a very tiny number. So a number that's close to 0, but that is positive. So that would mean maybe like 0.00001. If I divide 1 by something that's really tiny, I'm going to get a very large number. And because that tiny number that I have is positive, the very large number that I get by dividing by that tiny bit is going to be equal to something positive as well. Right? So if I divide 1 by something tiny like 0.0001, what I'm going to get is 1,000 or 10,000, I think I said for numbers after the decimal. So the idea is if I divide by something really tiny, I get something that is really large. And because in this particular case, I have that both the numerator and the denominator are positive, that number that is really large is going to be plus infinity. Show of hands if you now understand
how did you get negative infinity at the top?
Oh, that comes from this.
Oh, okay.
Right? So that comes from the fact that when x goes to 0, the logarithm of x gets smaller and smaller and smaller and smaller, which makes sense because if e to the power of something gets close to 0, that means that the exponent that you're putting on the exponential is going to be more and more negative infinity, right? So it's going to get closer to negative infinity.
All right.
Okay. All right, so we have minus infinity over plus infinity, which now means I can actually use L'Hopital's rule. And so I'm going to get the limit as x goes to 0 plus, and I'm going to do the fun part, which is to actually find the derivative of the numerator and the denominator. Derivative of the numerator is 1 over x, and the derivative of the denominator is negative 1 over x squared. All right, so at this point, I could try plugging in again, but this looks like I'm going to be able to simplify it quite easily, right? So what I can do is I can say, well, this is the same as the limit as x goes to 0 plus of 1 over x divided by minus 1 over x squared, which is the same as putting a minus in front of this all, and then multiplying this by x squared over 1. Okay? So if we divide by a fraction, it's like multiplying by its inverse. And so we're going to have that this factor of x can cancel out the 1 at the bottom, and this is the same as the limit when x goes to 0 from the right of minus x. And if this is the limit as x goes to 0 of minus x, then this is going to give me 0. Which, after all this work, makes us conclude that the limit when x goes to 0 from the right of x times ln of x is equal to 0. Can I see a show of hands for those of you who understand? Good. Okay, good. All right. So I'll give another. Here's the deal. I have another 2 examples that I want to cover today. So I think I'll just do those 2 examples. I don't think it should take too long, and then we'll finish class right away. Instead of my like the other option is I give you 10 minutes of break and then I like take your time up until 10:20. But what we can do is just finish these 2 problems and then you're free to go. And if you have questions about web work or homework or anything, then you can just stay and I'll answer your questions. Who thinks that finishing in one go is a better idea? Please raise your hand. All right, clear majority, so that's what I'm gonna do. Just finish the next 2 problems and then we can go. So the next problem is the limit as x goes to plus infinity of x times e to the power of minus x. All right, so as usual, we're going to try to evaluate this. Okay, so first thing is, if x is going to plus infinity, then I'm going to get something that is plus infinity, right? Because x is going to plus infinity, and so x is going to plus infinity. It's just, yeah, so it's just like truth. And then I'm going to have e to the power of minus x. So this is why I said that it was important that you also know the graph for the exponential function. And that's because, so the exponential function looks something, oops, the axis goes like this. So you all know that the exponential function is equal to 1 when x is equal to 0, right? So e to the 0 is equal to 1. And then the larger the exponent, the larger the value of e to the x is going to be. So this is going to look like this on the right side of this. So the larger x gets, the larger e to the x gets. Maybe I'm going to call it something different, t. So the larger t gets, the larger e to the t gets. Okay. But then if I take e to the power of minus something, that's like saying 1 over e to the power of something. And so the larger and negative t gets, so the more this gets to a large negative number, closer this is going to get to 0. Does everybody understand that? Usually there's no wiggling like that. This is just an artifact of me not being able to draw on the board. And so that means that if x is going to plus infinity, then e to the minus x is like e to the power of minus infinity, or the limit as x goes to minus infinity, which means that if I look at the limit of the exponential as the argument of the exponential goes to minus infinity, I'm going to get that this function is going to get closer and closer to 0. Right, and so this is times 0. Can I see a show of hands for those of you who understand this? All right, good. Okay, so again, I'm in one of those cases where I'm going to have to write one of these as a fraction or in the denominator. But this actually should be fairly intuitive to look at because I already have an exponent over here that is minus, right? So because I already have that minus in the exponent, what I'm going to do is just bring the e to the x to the denominator, and then I'll have a fraction. I'll have a numerator and a denominator, and I'll be able to differentiate each one of them. Okay, so I'm going to rewrite this limit as the limit when x goes to plus infinity of x, and then because this was e to the minus x, I'm going to write this over e to the x. Show of hands if you understand this. Okay, pretty good. And so if I try to plug in here, I'm going to get that as x goes to plus infinity, x goes to plus infinity, of course. And as x goes to plus infinity, so if x is approaching a very large number, let's say x is a million, a billion, trillion, whatever it is, then e to the power of a very large number is going to be a very large number itself. Right? And so now we're going to have, because this is infinity over infinity, I know that now I can use L'Hopital's rule, and I can take the derivative of the numerator and the denominator. So this is limit when x goes to plus infinity of derivative of the numerator, which is just 1, divided by derivative of the denominator, which is just e to the x. And this is just going to be 1 divided by e to the power of x when x is really, really large, which is something that's very large as well. Again, if I have one apple and I divide it by many, 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 many people, then each person is going to get just one tiny bit, right? Which is essentially like saying that each person is going to get 0, right? And so what this means is that limit when x goes to plus infinity of x times e to the minus x, this is going to be equal to 0. Juliette, Radu, and Savannah, you still have your hands up?
Yeah, why does every problem we've done so far equals to 0?
That's just that's just a fluke.
Okay.
Yeah, but like for example, here we could do the same thing if we had, let's say, instead e to the x divided by x, the result would be plus infinity, right? So results that are going to be very frequent are going to be 0 and plus or minus infinity. That's going to happen quite frequently, but it's not necessarily the case. In this case, it's just because I want you to see different types of problems, and it has just happened to end up always being equal to 0. That's it.
It looks like a pattern, but okay.
It's not. So just don't expect to be 0. The next one is not 0, so you'll be able to see that. All right. So last example for the day is e, which is the limit as x goes to 2 plus of 2 minus x minus e to the x minus 2 divided by x squared minus 4. All right, so I'll give you 3 minutes to finish writing and start solving this problem, and then I'll give the solution on the board, and then you're free to go. But again, try to do it on your own. This is your time to do homework, the time to practice on your own. Use it wisely. Okay, so for this problem, the first thing, for this problem and for every other problem, the first thing that we need to do is always to try to plug in the value of x. So if I try to do this, wait a second, 2 minus x, what? Oh, guys, I'm sorry. This should be a 1 after all of that. Okay, so this should be a 1 because otherwise you would have found something when you plugged in that you shouldn't have found. If you try to plug in, you should have found -1/0. Is that the case? Who tried to plug in and found -1/0? If you did that, you did the problem right. I just wrote it wrong. So that's perfectly fine. Now try to do it with 1 minus x. And if you had found the derivative without trying to plug in first, that was a mistake, but you would have gotten what I was actually trying for you to get. Okay, so this is 1 plus, and then, no, that doesn't make any sense. Okay, I don't know what's going on here. Let me just, give me a second. So no, this should be 3. There you go. Yeah, there you go. That should be the case. All right, so I'm going to solve the now corrected problem because that's the way that it should be. So the limit when x goes to 2 plus of 3 minus x minus e to the power of x minus 2 over x squared minus 4. If you had solved the original problem that I wrote down, you would have gotten -1 over 0. And the 0 over here would have been 4 plus a bit minus 4. So this is plus. So the final answer would have been -infinity. Okay. So that's just solving that problem that I miswrote on the board. Now I'm going to solve this problem because this is the one that actually needs L'Hopital's rule, otherwise I don't need it. And here it goes. What I'm going to get is the limit of this is going to be 3 minus 2 minus e to the power of 0, which is going to be equal to 0. And then this divided by 4 minus 4. Which means I'm going to have that this is 0 over 0. Okay, so with the corrected problem, remember, just change the value of this one. If this is the case, then I'm going to have 0 over 0, which means that I can't actually evaluate this right away. I need to actually use L'Hopital's rule, and I'm going to have, this is the same as the limit when x goes to 2 plus, and I'm going to find the derivative of the numerator and the derivative of the denominator. So, okay, guys, no, this is, I'm all messed up. This is, you can forget about this problem. I think my signs are all wrong. I think I corrected this too fast when I was preparing the problem. Forget about this problem. It's a lot easier than this. Sorry about that. You already have all the tools. This was just like a toy example in which I wanted you to find 2 derivatives, but I did this too fast and there's too many typos in my and I worry that I'm going to confuse more than that. Sorry about that. That's all for today. I think I've reached the point where it doesn't make any sense that I'm trying to teach anything because I'm getting more confused than I'm actually saying. All right, so is the idea, the general idea of this section more or less okay for everyone? If so, please raise your hand. Okay. All right, so that's good.